Let me give you this guy. How about this? This is a famous one. How about n goes from 1 to infinity of sine n over n squared. We're going to keep it simple. All right. Now, hopefully you're looking at this thing and you're like, well, I don't know. Could I do the limit comparison test? But what am I going to compare it to? Because sine's all over the place, right? Sine, we grab these values for the sine in from a, a curve that does this. It's positive, it's negative, it's not always positive, it's not, there's no reliable way to determine when it's going to be positive and when it's going to be negative. It's clearly not an alternating series test like I showed you before, right? But watch this. All right, let's look at the sum as n goes from 1 to infinity of the absolute value of the sine of n divided by n squared. Okay? Let's look at that guy. Now think about that. We know that the absolute value of sine of n is always less than or equal to 1. Right? Because it's sine. We know the range of sine is from -1 to 1, and if I take the absolute value of that, excuse me, then it's between 0 and 1. Right? No doubt about that. Okay, so what can I use that for? Doesn't that imply that the sine of n, the absolute value, over n squared is always less than or equal to 1 over n squared? Right? We know that the sum of 1 over n squared, as n goes from 1 to infinity, or from who cares to infinity, we know that this guy converges, p equals 2. So this implies by the comparison test, we know that the sum as n goes from 1 to infinity of sine of n, see what I'm doing here? I'm using a series of tests to be able to prove that the absolute value of sine n over n squared converges. Now, why was that useful? Well, we got one more I to dot. Remember I said proving series converge is a lot like lawyer math. Since the sum as n goes from 1 to infinity, the absolute value of sine n over n squared converges by the Ab's convergence test, we know the sum as n goes from 1 to infinity of sine of n over n squared converges, but it doesn't just converge, it converges absolutely. Absolutely. Since the absolute value of the sequence, remember the sequence just produces the terms, since the absolute value of the sequence produces a series that converges, that implies that the series is absolutely convergent. Now, wrap your brain around that a little bit. Why is that useful? Why is that powerful? Well, for no other reason, it gives you another tool. It gives you another arrow in your quiver as far as being able to prove that something is convergent or divergent. I guess it really doesn't prove that something's divergent, does it? Because, like I said over here, let's change colors. Like I said over here, this guy we know converges, but this guy diverges. And when we took the absolute value, we got this information. So if the absolute value diverges, we don't have any information. But if the absolute value converges, then we know that the series itself converges. And not only does it converge, it converges absolutely, which is pretty interesting. Okay, now buckle your seats, because the next test is absolutely, no pun intended, fantastic. Just a couple more minutes. I appreciate your patience. I'm going to give you the ratio test. If a rainbow didn't shoot out of your computer when I said the ratio test, there's something wrong with your computer. Have it checked. I don't know, run some virus software. I'll see you back. All right, here comes the ratio test. I'm going to give it to you, and I'm just going to let you chew on it for a sec. And then I'm going to we'll do some examples tomorrow in class. They don't take very long, and they're pretty fun to deal with. The ratio test is so simple, and even the idea behind it is so simple. It's very, very cool. You ready? Here we go. If the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n equals a limit which is less than 1, this implies that the series a sub n converges. Now, it doesn't just converge, it converges absolutely. Now, I'm going to write the test out because I know there are brains out there going, wait, what, where, who, how? Okay, just chill, relax. if the limit as n goes to infinity of absolute a sub n plus 1 over a sub n is equal to L, which is greater than 1, this implies that the series a sub n diverges. It's a wonderful piece of information. I'll explain why in just a sec. You may already have a sneaking suspicion. If you, now notice we got less than 1, we got greater than 1. You're just begging the question, what happens if it equals 1? If the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n equals L, which equals 1, bleh, wrong test. Do something else. Wrong test. It doesn't work. Okay? Now, go ahead. Think about it. Why is this true? Well, what are we really doing? We're taking the ratio of the sequential terms, a sub n plus 1 and a sub n, but as they go to infinity. So really what we're saying is what does this series start smelling like way out at infinity? Well, if I take a sub n plus 1 and I divide it by a sub n way out at infinity, and I get a number, I get a ratio, wink wink, that's less than 1, then doesn't this thing behave a whole lot like what? A times r to the n, where r is less than 1. It smells like a geometric series. It starts behaving like one. Now, I'm not claiming that it's going to be a geometric series, but the property that made a geometric series converge is the idea behind why the ratio test proves that if this limit of this series, of this sequence is less than 1, then what we're doing is way out at infinity, each term is like multiplying the term before it by a number less than 1. That's what it's saying. Think about that. That's exactly what would happen. Now, once you've got that little nugget of knowledge in your brain, this part is self-explanatory. It's almost as though, it's not the same thing, but it's almost as though the ratio, if I divide to get from one to the other, I'm actually multiplying by a number greater than 1, which should make this thing diverge. And sometimes it can be really hard to determine kind of the behavior of these series when you're way out at infinity. And then, of course, when it equals 1, we're kind of screwed. We don't have enough information. The obvious case of that would be like if I took the sum as n goes from 1 to infinity of 1 over n cubed. Now, we know that this thing converges, right? We know that it does. But watch, if I try to use the ratio test on this, if I take the limit as n goes to infinity, what will I get? Well, a sub n plus 1, that's 1 over n plus 1 cubed over 1 over n cubed. This is equal to the limit as n goes to infinity. If I do my extremes by my means, I get n cubed over n plus 1 cubed, which is equal to 1. Well, it converges, Ripley. Why can't we say it converges? Well, isn't the same thing true if I take the limit as n goes from 1 to infinity of 1 over n, which would be the limit, if I want to use the ratio test, right? The limit as, I should use implies. I'm speaking the language badly. You guys should yell at me about this. Limit as n goes from n to infinity, the limit as n goes to infinity of 1 over n plus 1 over 1 over n, which is equal to the limit as n goes to infinity of n over n plus 1. Ah, crud, which equals 1. So what I have is I have a case where I use the ratio test, I equal 1, and I converge, but I also have a case where I use the limit, or the ratio test, excuse me, it equals 1 and it diverges. And in mathematics, one exception and you're dead. You're screwed. Okay? So tomorrow in class we'll play with some of these. These are really, really helpful and they're pretty darn fun too. Thanks for listening to me. Have a great day and I'll see you in class tomorrow.